Welcome to the first of 4 Physics 30 review videos. In this video we'll be looking at Unit A, Momentum and Impulse. This unit essentially dealt with collisions and how to mitigate the effects of those collisions. So momentum is the quantity mv, impulse is F net delta t. So momentum is conserved in isolated systems. What does that mean? If we've got 4 units of momentum before a collision, we end up with 4 units of momentum after a collision as well. So we looked at 1D collisions and 2D collisions in this unit. For 1D collisions, the initial momentum is equal to the final momentum. We've got no x and y to worry about, so there's no trig required here. Everything happens in one line. The main thing, though, to focus on is that the initial momentum is equal to the final momentum. For 2D collisions, momentum is conserved in both the x and y directions, so when we're solving problems, we'll have to deal with 2 sets of equations. One for the x information, the other for the y information, so there's a bit of trig required. We divided collisions into one of 2 categories in this course. Elastic collisions are ones where the initial kinetic energy is equal to the final kinetic energy. A standard billiard ball collision is possibly the closest example of such a collision that you may be familiar with. Inelastic collisions, on the other hand, are ones where the initial kinetic energy is greater than the final kinetic energy. A hit and stick collision, like these football players on the left, is a pretty common example of an inelastic collision. The vector quantity F delta t is called impulse. It's equal to the change in momentum, and F refers to the average force. So if the momentum is going to change by some amount regardless, you might as well spread it out over a longer time to reduce that average force. It's why we have airbags, and hockey helmets, and crumple zones, and shin pads, and all that other stuff. So let's get into a couple examples. Alright, here's a question from page 505 in the textbook, number 59. We've got a red bocce ball traveling in at 1.8 meters per second north. It hits a smaller blue ball, and then the blue ball goes off at 0.485 meters per second, 84 degrees west of north. So the first part of the question asks us what the velocity will be of the red ball immediately after impact. So before the collision, the red ball goes up north, strikes the stationary blue ball. Afterward, the blue ball goes off towards the left, 84 degrees west of north, and the red ball goes off in some unknown direction. So that's part of what we want to find out. So there's the 84 degrees west of north, and that direction is part of the velocity calculation of the red ball. So because this is a 2-dimensional momentum question, we're going to need to deal with the x components and the y components separately. So starting with the x components, we've got the initial x momentum is 0. So left and right there's no movement in that direction, so it's 0. And the final x momentum is also 0 because momentum is conserved in the collision. So the final momentum is equal to the momentum of the red ball in the x direction plus the momentum of the blue ball in the x direction in the final. So after the collision, that's what the primes are. So 0 is the final momentum, and we'll just write down the mass of the red ball, multiply that by the speed of the red ball after the collision. And that's what the prime there is for. And we add the mass of the blue ball and multiplied by the, there's a kilogram, multiply it by the speed of the blue ball in the x direction. So we're going to take a x component of the 0.485 meters per second value. So we're going to use cosine of 174 and multiply it by the speed of the blue ball total. So we're using the polar coordinate angle measure. So this is where we get the 174 degree from. It's just nice because the signs work out nicely. So hopefully you'll see that in a minute. But you can use 84 degrees too if you like. Just gotta keep track of that kind of stuff. So same as above, and that second portion of the equation gives us 0.699 kilograms per meter, or kilograms times meter per second. Okay, so then we add 0.699 to both sides, and some digits after that, kilogram meter per second, and that's equal to the stuff above. So we get the x component of the red ball's velocity after the collision. So it works out to about 0.055 meters per second. We'll shrink that away and move on to the y components. So the momentum is conserved along this direction as well. So what we have initially in the y direction for the momentum before the collision, all the momentum is found in the red ball. So initially the red ball is all y component. So the mass of the red ball is 1.26 kilograms multiplied by the initial speed of the red ball, so 1.8 meters per second. And it's all in the y direction, so this is where we're getting this from. So that works out to about 2.268 kilogram meter per second. So because it's conserved along this direction, it's going to be the same after the collision. So 2.268. Now it's just going to be split up between the red and the blue ball though. So 2.268 kilogram meter per second. Same after as it was before because it's conserved. The momentum of the red ball after the collision, the mass doesn't change. We want to find out the speed of the red ball in the y direction after the collision. So that's that variable. And add the momentum of the blue ball after the collision. So we know that. We've got its mass, the 0.145 kilograms, and multiply that by the speed of the blue ball in the vertical component. So we're going to do sine of 174. So again, we're using polar coordinates there, just because it works out nice. So same as above. And the result of that last bit of calculation is about 0.00735 and some other digits, kilogram meter per second. So we subtract 0.00735 from both sides. That red bit is the same. Figure out what the left side is there on that step. Divide both sides by 1.26. And we get the final speed of the red ball in the y direction. So 1.794 meters per second. So now that we have the x and y components of the red ball's velocity after the collision, we can find out the magnitude of the red ball's velocity after the collision. So we use Pythagoras theorem. Take the x component of the red ball's velocity, square it, add the y component of the red ball's velocity, square that, and then square root it. Okay, yeah, square root. So this will give us the final speed of the red ball, so post collision. So the inside there we get about 3.22 units on that guy are meters squared per second squared, and when we square root it, the units will work out to meters per second. So the magnitude of the red ball's velocity after the collision is 1.795, some other digits, meters per second. So sig dig wise, 1.8 meters per second. So next, because we're finding the velocity, we need to find the direction as well. Okay, so we do opposite over adjacent. So we use tan, and we just take the y component of the red ball's velocity after the collision, divided by the x component of the red ball's velocity after the collision. So we take the inverse tan of that ratio. So from what we found before, 1.794 divided by about 0.055 Yeah, I've got these values stored in my calculator, so anyway, we get theta is about 88.23 degrees. Right, shrink that away. So now we can find the velocity of the red ball after the impact. We've got both the magnitude and the direction here now. So 1.8 meters per second is the magnitude, and about 88.23 degrees is the direction. So that's polar coordinates. And keeping consistent with sig digs, I guess we should express that as maybe 1.8 degrees east of north, or maybe just 88 degrees in polar coordinates. Okay, next thing we need to do is to determine if the collision is elastic or not. Yeah, wrong kind of elastic. So we just need to compare the kinetic energy before to the kinetic energy after the collision. So I'm using the prime notation to indicate after. We could also use this notation if you prefer, or that's often used as well, but I'm just going to stick with the prime notation that we use in part A. So kinetic energy formula from the formula sheet is that. We were given the blue and the red ball speed before the collision. We found the red ball speed after the collision, and we were given the blue ball speed after the collision in the question. So beforehand, before the collision, the total kinetic energy is the red plus the blue energy. So let's plug in some values. 1.26 kilogram for the red ball. Speed of the red ball is the 1.8 meters per second. So square that, don't forget. 1/2 plus 0.145 kilograms for the blue ball. But the speed of the blue ball is 0 before the collision, so the second term just disappears. So total kinetic energy beforehand is just 2 joules, and that's 2 significant digits. So after the collision, the total kinetic energy is again the sum of the kinetic energy of the red ball plus the kinetic energy of the blue ball. Keep in mind we're using different speeds after the collision. So there's the values. That 1.795 is still stored in the calculator. And plug in the values for the blue ball. So then we end up with 2.05 roughly for the red ball and 0.017 for the blue ball. So round that to 2 significant digits. It's 2 joules after the collision, total kinetic energy. So now we compare the kinetic energy before the collision with the kinetic energy after the collision, and they're the same, so the collision is elastic. Okay, so we've got an impulse momentum question here for you. A 57-gram tennis ball flies in 14 meters per second north. It struck and returned to the southern opponent after it struck. So we've got a force time graph of that event, and part A is asking for the magnitude of the impulse. So we just got to find the area under that graph. And what is the area of a triangle? 1/2 base times height. And that's on your formula sheet. So just put in the values, 1/2. The base is 6 milliseconds, so times 10 to the minus 3 seconds. And then we multiply that by the height, which is 600 newtons. And that gives us 1.8 newton seconds. And we're basically done at that point because it's asking for the magnitude of the impulse. But I'll just give, so impulse, it's a vector quantity, so I just figured I'd pepper this in anyway. So it'd be 1.8 newton seconds towards the south, because that's the direction of the force, right? All right, so shrink that away onto part B. So part B is asking for the speed of the tennis ball immediately after it's being struck. All right, so we'll define the north direction as positive and use this formula, which is on your formula sheet. So F net delta T is M delta V. So we found the impulse from part A. slap a negative sign on that because it's going towards the south. The mass of the tennis ball is 0.057 kilograms, and the speed difference, or the speed change, is the final speed minus the initial speed. Initial speed is north, so we slap a positive on that. Okay, divide both sides by 0.057, and we get negative 31.57 meters per second on the left, and we're left with BF minus 14 meters per second on the right. Add 14 meters per second to both sides, and we end up with negative 18 meters per second. And because it's asking for the speed, we're done at that point, but I figured I'd just throw in the vector here for fun. 18 meters per second south. So that's the speed of the tennis ball after it's struck. So please note that the F net mentioned in this equation gives us the average net force on the tennis ball. So what that looks like on the graph, it's 300, the peak force is there, they're different.